much for showing up for this talk. I know it's in December, cold, and one want to dash out and get some Christmas shopping done. However, you're here to hear me talk about structural glass. A bit about me first before we go into that. I am a practicing structural engineer, have been chartered since 2000. But before that, I've been working in the field since 1987. I was a technician and I went to university, etc., etc. So quite a long sort of career, really, and it's mainly been certainly in my training when I was working at Duos Macfarlane, which is a practice in London, in North London near Camberwell Street. They specialised in structural glass, which I'd never encountered before. And it was like a rite of passage, really, for every structural engineer who worked at Duos Macfarlane, that they had to design in structural glass at some point. And I was there for 3 years, so I certainly encountered a lot of structural glass then. I then eventually moved on to Mount Macdonald and worked on projects like the Sage Media Centre and Wembley Stadium. From Mott, I now work for the Institution of Structural Engineers as a structural engineer and their technical advisory or technical engineering team. And we are producing original content for the industry and for you. You may have noticed the first fruits of that when we actually wrote the technical guidance notes in Structural Engineer. That's all me. That's me writing those. There's about 45 of them now. And the last one of the level ones of technical guidance notes will be on structural glass, so because I wrote this. So without further ado, let's move on. Why did we write the second edition? Because there was a first edition of this book back in 1999, December 1999, so 14 years ago. And this is the cover. And a lot has happened in those 14, 15 years or so. The biggest thing was new technologies have arrived. Century glass, which is a form of laminate, ionoplast laminate, didn't exist really in 1999. It was just invented at the lab in 98, so it barely was even adopted. So the first edition doesn't even mention this, yet this is now pretty much an industry standard laminate. I'll explain why that is soon. Introduction of limit state. Now there is mention of limit state in the first edition, but it doesn't really go into details about how to apply it. Now, the European Eurocodes are actually developing not a code of practice quite yet, but it is a method for designing structural glass using limit state theory. So using the same partial factors that you use in EN 1990, you can now apply to glass using these papers, using these methodologies. They are draft methodologies. They are not codes of practice, but I'll come to that later. But it's this draft, the authors of which helped us make this new text, has been infused completely within this new second edition. We've adopted this methodology wholesale, pretty much. And the last thing, of course, pretty obvious, structural analysis in computing has just skyrocketed since 1999. People's laptops, indeed their mobile phones, are more powerful than the computers back in 1999. So clearly we've had to address that rather robustly to the point where we've now dedicated an entire chapter to that subject. So what's in the second edition? What's changed? What's different? Well, there's design principles. We talked about methodologies, but we also talked about the basic issues of we have large deflection theory as opposed to simple deflection theory. We have to have large deflection theory because typically glass deflects more than its thickness, which means that you can't use simple deflection theory because if you do, everything becomes conservative. Design criteria. So this formula, so you'll see this later on again, but this is the core of the draft methodology, this equation here. Looks a bit frightening, but actually it's fine. It's just lots of variables. You've seen them all before. One's like that anyway. Then we talk about analysis of structural glass. I do love this photograph and this image. The image on the top is the box, there's a glass box that was rebuilt for the Apple store in New York. And there is the box. There was a box there originally, but they rebuilt it and they got rid of all the additional. It was basically too fussy, and Apple said, "Can you make it clearer, please?" So they did, and they made this. And there's an entire chapter dedicated to this one, not particularly this particular case study, but the concept and the ideas behind what the things you need to do specifically when you're analysing glass elements in computer programs, which is generally the favourite thing to do because of the nature of the material, which I'll talk about later. Then we talk about element design. This is one of the images that I drew in the guide. This is like a full sort of distorted image showing the laminate of a glass beam, and in the middle the pane's not lining up. And this is the problem with laminates. You can't actually get them to line up properly even when you build them. But there's also elements on. There's a whole chapter dedicated to explaining how each type of element is designed. Floor plates, balustrades, columns, walls. It's all in there as a single chapter, chapter 8. So if you want to know how to, and it's all divided up in that way, because that's something that the task group wanted to have. They wanted this text to be more than anything a design guide on how to design in glass. That's what they wanted it to be. They wanted it less discursive, less descriptive, and more of an actual practical guide on how to use structural glass. And I think we've achieved that. We also go on about connection design. This is a connection of a glass bridge in Cheapside, 150 Cheapside. Extraordinary glass bridge. It's actually, there's an image of it in the book. And this sort of illustrates the various different clamp details and sections that you have in glass. And we'll talk about localized stresses and that's the big driver behind connection design. Fire protection. You have to fire protect glass. Glass with regards as a sacrificial thing, but it can, in some cases, arrest the movement of air and heat and what have you. So it can actually use as a form of barrier, even though it melts. But there's lots of studies and lots of talk about in the text, explanations about how you can actually actively protect glass, and also how glass really reacts when it encounters temperature rising. Extreme loading conditions like bullets, that sort of thing, also seismic effect, and also blast loading as well. That's a really hot topic, especially when you're dealing with train stations. I've designed I did Farringdon train station, and I had to deal with blast loading, and there was glass balustrades and that sort of thing in that station. So that's again a whole chapter dedicated to that one topic, accidental loading, if you will. Then we go one stage further. We actually go into procurement, construction, and maintenance. So the actual, what things you need to know specifically about how big panes of glass can you really get away with? What things additional things you need to know about buildability before you start designing structural glass. So we talk a lot about that, and that was written by a contractor. We actually had there's members of the steering group. He said, he put your hand up and said, "Look, let me write this." He said, "Fine, we will let you write it." And then finally, inspection. So this is quite common. A lot of structural engineers do get called out on glass elements where they like balustrades and that sort of thing. A lot of us have scratching head like, I'm not really familiar with this material. Ultimately, you've got to understand, as I'll explain later, it's very, very brittle. It's very, very strong, it's very brittle. Now, this looks like a certain type of failure. If you look at the lower image, this one here, it looks like a certain type of failure. You might have heard of nickel sulfide failure, where you have small particles of nickel sulfide within the glass. You can't avoid it, it always exists in glass, and over time, 5, 10, 15 years after it's put in, it expands and explodes. And when it does that, it has this little butterfly sort of image, which looks a bit, sort of leading you on here, like that. This isn't one of those, this is actually impact. It just happens to look like a nickel sulfide failure. I've had the client kind of confused. So, let's get into the nitty-gritty. So that's the contents of the report. Very, very, very comprehensive. There's way more in it than I've just listed there. There's a whole section on the history of glass, which we didn't know where to put. We were going to put it in an appendix, should we put it at the beginning, but we actually ended up putting it right at the beginning. You can read it if you like, it doesn't matter. But chapter 2 goes on to the meat of actual what glass really is, which is what I'm going to talk about now. So we have basic annealed glass. It's always prefixed with the word basic, apparently. But yeah, annealed glass is the base glass that everyone makes. And then there's heat strengthened glass, which is a form of pre-stressed glass, but it's not quite as strong as toughened glass. But it is stronger than annealed glass. So why have it? Well, it breaks just like annealed glass. And this is actually a strength of it. These large shards that it creates when it breaks, and also these large sections. This is going to come on later in the worked example I'm going to show you towards later on in the lecture, is how important it is in terms of safety and how it actually it's something you should rely on when you talk about the failure of glass. Then there's thermally toughened and chemically toughened. Breaks like this. Huge clumps of dice, it explodes. The reason being, it breaks very, very differently to to anneal glass is because of this. Thermally toughened, it's a little weaker, but it does have a thicker layer of outer compressed extreme fibres as opposed to inside. Whereas the chemically toughened is very, 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 very thin, which means that it's very difficult to actually have any enamelling on it or any kind of treatment to it. And if it's scratched, even slightly, it can actually explode very, very quickly, very easily. Whereas in thermally toughened, it doesn't suffer so much. So that's something to be aware of. And also, chemically toughened is really expensive. So something to be aware of. And finally, you might have heard of heat soaking. People can get confused with this, thinking it's like heat strengthened. It isn't. Heat soaking it's actually a process that's used to reduce the risk, not eliminate, reduce the risk of nickel sulfide failure, which is what this looks like. You notice it's got a little butterfly thing there. Little butterfly. It's a single little crystal particle and cause that paint to just go bang, just like that. And the way it does this is that basically heat, when the glass is exposed to heat or temperature changes, these particles or these crystals grow. So you can simulate these conditions by putting the thermally toughened or the toughened glass through the heat, through the oven again. That's what heat soaking is. You just put it through again and just replicate and see if it will fail. And if the glass has failed, there's too many nickel sulfide. So that's what heat soaking is about. It's about reducing the risk. It doesn't eliminate it though. I mean, it reduces the risk significantly by a factor of 100. So let's talk about glass behaviour and what it does and what it's about. So it is actually quite strong. Here's some numbers for you. So basic annealed has got 45 newtons per millimetre squared. Heat strengthened is 70 and toughened is 120. This is characteristic strength, and these are actual strengths used in the methodology that I mentioned earlier in the Eurocodes. But it is brittle. In a sense of understanding what I mean by this, in the sense of steel. Steel, as you know, is plastic, so it can actually go to plastic yield. So everyone has seen this graph. And then we superimpose the same thing, only for glass, and it looks something like this. It doesn't. It is. That's what it does. It doesn't. This is something it sounds stating the obvious. Chris is stating the obvious, but this is the core of when you're designing glass. It doesn't yield, and when it breaks suddenly. But it is very, very strong. It's also stochastic, which basically means it's random. The nature of the failure is quite random. This is a series of tests, as you may be able to read from there, probably can't. As a result of 740 tests on 6mm annealed glass using PRN 1288-2 test method. There's a whole raft of test methods for glass, which I'll explain later. But ultimately, the samples were taken from 9 European factories. Now look at it. Look at that spread. It's all over the place. So it's unpredictable when really it fails. So its factor of safety is very high. And the characteristics, the bending strengths I gave you, incorporate all the data that you see there in that stochastic chart. And it is very, very sensitive to local stresses. This is an image taken from chapter 4, which is about design of analysis of structural glass, both as a large model and also localized stresses. You can see the angry red around the bolt hole there. So, laminated glass. This is a core thing that happens in glass, because one of the odd things about glass, and I'll talk about it in a worked example, is that you have to consider when it breaks, when it fails completely. And it has to be a redundancy in it to what happens when it fails, because I already showed you a graph earlier, because when it fails, it's sudden. So you have to, what they call the failure condition. You have to allow for a failure condition in your analysis and design. So it's to ensure that if something does fail, there's some redundancy there too, so you can replace it, what have you. And one of the things you can do is actually make it laminated. So if one of the pliers goes, that's okay, the rest of the pliers are holding it all together. So if laminated glass first appeared in building structures in the 1970s, but actually laminated glass actually as a technology existed in the late 1800s and in the early 1930s. It wasn't until the 1930s when they developed PVB, which is polyvinyl butyl this is the industry standard almost, at least it was up until very recently, for laminate, and it's waterproof. That's what's great. But coming up in 1998, Century Glass, which is a trademark name for DuPont, they invented this stuff. It's ionoplast laminate, and there's a little chart that gives you why people like it so much, and structural engineers specifically. The little red line at the bottom of the chart is PVB. The black line above it, sailing above it, is Century Glass. You can understand what these charts mean. This is the top chart is at 20 degrees C, and the lower chart is 50 degrees C. So temperature has a major detrimental effect to laminate, so especially Century Glass. But so there's that issue. But also time has an impact. If you look at there, it's got 3 seconds, 1 minute, and the actual chart on the vertical axis, the shear modulus of the laminate. So as time goes by, in 10 years, it's almost, may as well be the same as, well, not quite, but it's not as great as well, it's almost as weak as PVB, but also it does actually deteriorate so much that it eventually becomes the same as PVB, which makes people go, well, it's fine, but if I've got a design life for 50 years, it may as well be the same. But there's that argument. Even still, people do like this stuff. TPU. This stuff is great because you can use polycarbonates. You can use it to fix polycarbonate, which is great for security glass and that sort of thing, because it resists impacts and bullet attack and that sort of thing. Polyester, PET. This allows for LEDs to be installed into laminates, and you get things like that. Pretty. And then finally, you can use resins as well, in sheets and that sort of thing. That's quite historical, but it's very similar. Resins is pretty much the same as PVB. The only unique one out of that is pretty much Century Glass, and you come across it more and more and more. It is significantly more expensive than PVB, as you'd expect, but like I said, its high shear modulus gives it a lot of credence of use. So, I'm now going to introduce you to these two documents that now exist. You can get them from the BSI. Oddly, they are open for public consultation, but they are charging for the right to use them, £10 a pop apparently. But nonetheless, PRN 16612 and PRN 16613, they are draft methodologies for determining the strength of glass, but they are not a code of practice. They are going to be used as a basis for developing a code of practice over the next 5 to 10 years. Here they are. Okay. Now the top one is more core than the bottom one. The top one really deals with the design or the determination of strength of glass, whereas the bottom one deals with how you deal with the composite action of laminates or plies within a laminated glass, which we'll talk about later. So they're based on these material properties. So these are like the core material properties that are the same for any type of glass, whether it's toughened, annealed, anything. So the characteristic basic base strength is 45 Newton for annealed glass. Its density is 25, so it's the same as concrete. Glass is very heavy. Young's modulus is 70,000, so it's not that. It's not as stiff as steel as you'd expect. And the shear modulus 28, and then Poisson's ratio is 0.22. These numbers again are coming to work example, but this is like the core. Everything, all roads lead to these numbers. So, in these codes, there's a series of variables that they throw at you. And FBK is the strength for pre-stressed glass, which is the toughened stuff. And there's different ways of actually making glass, there's enamelled, patterned, that sort of thing. This is all explained in the text. But ultimately, most of the figures use these ones at the top here. Okay. So FBK is a variable that determines the strength of the characteristic design strength, the characteristic bending strength of pre-stressed glass. And then we have these material factors, and this is quite interesting. For basic annealed glass, in the UK, they've deemed that 1.6 is a good figure for basic annealed glass. But if you look at these codes, the value of 1.8 is given. So the glass industry, in far the UK is concerned, oh no, we're going to have 1.6. So when this comes out as a UK, there's going to be a UK national annex that says that figure is going to be 1.6, not 1.8. So there was some conjecture about this, and we had a bit of a tiff about it, and ended up putting this disclaimer explaining this is actually that value. But the other value for surface pre-stress glass is always going to be 1.2. Oddly enough, also, if you notice, it's a very strange. The variable numbers, people did query why have we got semicolons in them because it's hard to write, but hopefully they'll go away. KSP deals with how the glass is finished and made, so if it's sandblasted or just produced off the rack. So this is about manufacture and how it's done, and this impacts on the structure. And then again, this is the orientation of the factory. So if it's a horizontal, there's no factor, but if it's a vertical system, you have 0.6. So you have to need to specify in your specification when you draw up structural glass how it's made, because you made assumptions on how it's made. And you can see 0.6. That's not small. So if you find your manufacturer is going to do a vertical orientation, you need to change your calcs. K-mod. Now this is very important because this is about the duration of the load. This impacts on the design of glass massively. If you can see here, 1 second gust on a bit of cladding, your K-mod is 1, so you pretty much ignore it. But if you've got someone walking on it, or if you've got its own self-weight, it drops down to 0.29. So understanding this table is also core to design of glass, because you understand that the duration of load, the impact of the duration of load is massive when you're designing glass elements. So this is how you determine the strength of a monolithic pane of glass. So not laminate, just a single pane. There's two basic equations. First one is basic anneal. Looks like that. Now I've already explained to you these various figures. So FGD is the actual design strength, not the characteristic. This is the design strength. So you've got K mod KSP, and then you multiply it by the FGK, which is the figure I showed you earlier, which is basically always 45 newtons per metre squared, and you divide it by the relevant local material factor, which is typically 1.2. But if it's pre-stressed, you add this expression to it. So you take your basic annealed, and then you add this expression to it, and then you get your design stress, the design strength, I should say. So if you notice, the only thing the only thing that changed, you've got FBK just there. There's your FBK, just there. But what about laminate glass? It's got to be working together somehow, isn't it? You can't just say they're dead weight. Sometimes you have to, but most of the time you can actually say there's some form of composite action, but typically it's only acting in a layered way. You have to assume that, because rather than acting completely compositely, in a long-term condition, you have to assume that the deterioration of the laminate happens over time, even for century glass, and you have to then make changes to your calculations. So you have to come up with an effective thickness. I'm sure you're familiar with that concept where the actual thickness is way bigger or thinner than what we analyse. So, talk about variable definitions. Omega is this variable, it's just shear constant that you apply, or factor that you apply to various types of laminate, and also various types of load. So again, the duration of the load has an impact on the factor you can apply. And if it's permanent load, so nothing. It's nothing. If it's snow loads, and there's different families of laminate. And again, it's all explained in the text, but this all depends on whether you're using EVA or all the ones that I listed earlier. So there's a bit of confusion here. There's two different types of effective thickness. The first one is effective thickness for deflection equations, deflection assessment. The second one is for bending. Okay, they're two different. And the code, well not the code, or the methodology I should call it, they've given these two different variable names for the same thing, depending on what you're calculating. So for HK, that's for deflection. For HJ, that's for bending. And this will be clear when I show the diagram. So HMI is actually a distance between the centroid of the laminate glass, the overall thickness, and the centroid of the glass pane, or the ply. Here's the diagram. A little bit confusing, but if you see, H1, H2 and H3 could be HK or HJ depending on what you're looking at. If you're looking at deflection, it's all the H1, H2, H3 is always HK. So basically, and there's these two equations to explain it even better. So deflection due to bending looks like this. I know it looks horrific, sigmas. Oh no. But it's really quite simple. It's basically you're working out the sum of HK. In other words, the sum of the thicknesses of each ply cubed. That's what it is. So say you had 6 mil, 3 times 6 mil laminate, it will be 6 cubed plus 6 cubed plus 6 cubed. So that's for deflection due to bending. And you'll notice the variable number is HEF semicolon, there it is again, W. Fine, great. So you look at bending stress, there's that variable again, HEF semicolon W to the cubed. Which means you have to work out your deflection bending effective thickness before you can work out what the effective thickness is for bending. So it's kind of backwards. But so even if you're not looking at deflection first, which very few people do, they have to work out that first before they can actually get to the bending stress. Again, this is all explained in the methodology, and I'm just sort of summarising here. So, worked example. I'm going to hand this out to you. So this is a worked example from the actual text that I worked up. There are worked examples in the first edition, but we said, no, let's just do brand new ones. Yay, go us. So this is what it is. It's a 1.5 or 1.5 metre floor plate with continuous support, so not particularly complex and very, very common in glass floors. There's an imposed load, or as we now call them, of course, variable action, QK, of 1.5 kilonewtons per metre squared, or 1.5 kPa, whichever wants to use. There's a concentrated force, QK, of 3 kilonewtons, which is as per BSEN 1990. It's a 3-ply laminated glass with PVB interlayer. The top ply is toughened, and the bottom 2 plies are heat strengthened. What I'm doing here is there's 2 durations that apply. So again, when you're talking about design and structural elements in glass, you've got to think about how long the load is going to be applied to it. Again, it's unique to glass because of it's very sensitive to that. So they actually pretty much have to design it twice. Actually 3 times, which is why this is 5 pages long for a single floor plate. So basically, so we do permanent condition first. So permanent action condition. So throughout the language of the book, actually, we do have a lot of Eurocode speak. So there's a lot of actions and that sort of thing, deliberately because it's based on the Eurocodes anyway. So we derive first thing we find out is what's our K-mod. That's the first thing you've got to find out. It's 0.29. And then because it's 50 years, because it's a permanent load condition, because you're taking the self-weight of the glass, you're ignoring the imposed load. And then, well, initially anyway, you're not actually designing it for that condition. And then you've got a whole raft of variable definitions there, just underneath that. And then you plug them into the equations I showed you earlier, and we get 29 newtons per metre squared. Great, that'll do. So that's the base design strength of the glass that we have to design. We have to make sure we don't exceed that. The next is we do the variable action on the short-term load, and then it's pedestrian. There's some conjecture about what that means, but we said, well, it's duration less than 5 hours, because you could have someone standing there for quite a long time. Could be anything, bits of furniture, anything. So you make it 0.6. Then we get 37. So notice, because it's a variable action, because it's a K-mod's much higher, you get 37 newtons per metre squared. But that's because it's a variable action, not a permanent one. So we've got 2 design conditions, 2 design stresses to design against, or design strength, I should say, to check against. The next sheet, we then talk about how we develop the effective thickness of the glass. We can't assume that the glass, each pane acts individually, and you can't assume it acts as an entirety. Because we've assumed, by the way, I've just noticed here, it's 3, we've selected 3 plies of 12 millimetre thick with a 0.76 millimetre thick of laminate. This can vary, but this is fairly typical thickness of PVB laminate. And, clearly, it's not 36 millimetres thick, it's much less than that. The actual thickness, when in terms of deflection, is 15.1 millimeters. You go down to the equation there, see all the derivations and explains what these variables mean. And we also had to ignore the shear factor omega because it's in permanent condition. We have to ignore it. Therefore, we only get 15.1. But when we do the variable action, we can include it. And then it goes up to 16.7. Then our bending stress, and then effective laminated glass for bending stress goes up to 18.7. So we've got all these different variables, all these different geometries of the material changing depending on the applied load. This thing's very complicated. You've got to think really methodically when you're doing this, when you're designing in glass, just because of these differences in the fact that we can't just say, well, it's a one load case, it's just the material, it's fine, it doesn't care about the duration of load. Whereas glass, it does. And then we go on to apply the concentrated point load. I believe. No, we don't. Tell a lie. This is we actually now we're going to apply the area load of 1.5 kPa. Now, one of the things in structural glass we do use a lot. We use Rourke's stress and strain formulas for stress and strain. I'm not sure if you're familiar with that book. For me, it's up there with W squared over 8, these equations, but they deal with plate design and stresses in plates. And they don't necessarily talk about glass, but they can be used for glass structures. And this is what we've done here. So if you want to know where does beta come from, where do these equations come from, they're not from any code, they're actually from that book. And we make lots of references to that book, and we do explain where all these variables come from. But this gives us a bending, applied bending stress. So when we get down to the combined loading, we're now down to the middle of the page on page 3 now. We've got 2.3 newtons per metre squared. Barely anything. And this is the UDL. And then we get the, then we use the variable action, and it's 6.4 newtons per metre squared, which is way less than 37.7. Okay, so is Chris over-designed this? Surely not. Well, we'll come on to that later. So, concentrated point load. This is where you have to simulate a concentrated point load in the middle of the glass. And again, we use Rourke's equations there at the bottom of page 3. Again, if you're not familiar with those, I do recommend you become familiar with them. They're extremely useful, not just for glass, but for other materials as well. And then we have this really, really long equation, which has even got log in it. But eventually, we'll get a value of 29.1 newton per metre squared, which is clearly pushing now. We've thought, oh, that is making sense. Still not quite over 37.7, but he's got 29.1. So then we do a deflection check. So this is all, and we're all assuming that the glass is all intact right now. It's quite important. We still think the glass is intact. So we do another series of equations to figure out what the actual deflection, what the actual thickness is when it's on deflection. It's 21.5 millimeters as opposed to 36, and about 37, I should say. And the deflects by 2.4 millimeters, which is way less than the 6 millimeters that's allowable for typically, which is standard depth ratio of 250 for a floor plate. So why is it so thick? It seems to be doing really well, but it's because of the post-failure effect. That's why it's so thick. Because if you go into the bottom of page 4, we then talk about how we design the glass as if 2 of the paints, not one of them, have gone. 2 of them. So we've only got 1 to resist it all. Okay, so we've got dead weight of the glass above, and we design it all again on page 5. And we go through the whole rigmarole, and finally we get to the concentrated point load for the imposed load right at the end. And there we've got 47.1 newtons per metre squared. A 12 mm thick plate cannot take that. Can't do it. Fails. So what you'll find is the critical design case isn't even in the actual permanent, like the intact case. It's actually the case where it's broken. And I did some, I hate doing it by inspection, but I actually made the plate 40 millimetres thick, and then that reduces the stress down to 34.6, which is okay. So that's really the key of glass, isn't it? You've got to worry about load durations, you've got to worry about, so that's the unique element of glass design, isn't it? You've got to worry about 2 things: load duration and post-failure condition. Because you've got to assume it's going to break, because it does randomly, as I showed you earlier, the stochastic diagram. thanks for listening, everyone, for your time and patience. No doubt you have some questions.
Sorry, Chris, thanks for that. It's very interesting. I suppose one thing I took from it is that you'll have to know exactly where your glass is made and how it's made.
Yes.
And every single piece of glass is different.
Yes.
That's why the factors of safety are so big. I suppose what I took from it is that if I was designing glass, I'd ring you. We'll take the quick questions, so I suppose Kieran.
Thanks for a very interesting lecture. I know there's a chapter in the book on computer modelling of glass, and I'd just be interested if you have any comments or what kind of advice would you give to the finite modelers in the room who might think about modelling glass with typical finite programs?
I think the big question we had argument, it was genuinely an argument, was how you model laminated glass knowing that its effective thickness is different to its actual thickness, therefore the self-weight of the model is different to the actual design thickness. So you had to do some fudging and making sure that there's some commonality between the two. That was the one thing. The other thing was support conditions. Model those accurately. Springs, everything, that sort of thing. You cannot, if you start assuming infinite stiffness in a glass structure, you might end up over-designing it or under-designing it, depending on the condition. But there were the two things: laminated glass, effective thickness. And there's a huge chapter about, section on that very issue. It's basically paraphrasing what we had the meeting discussion about, and I put it in. But yeah, we did wonder where to put it in the book. Should it be after the design examples, after all the handhelds, or before? And there was a big push for before because they thought it was so core. It's just as core as the explanation of the determining the strength of glass. It's part and parcel, so it's actually quite upfront. We made the navigation of the book relatively straightforward because then there's a lot of repetition as well. If you really cover to cover, you go, hang on, you said this already. Because people will pick up that book and go, I want to design the balustrade. It's fixed straight to the balustrade and just like that. That's fine, because the book's designed to be like that. It's like the manuals, the manuals of concrete and timber, and same thing. You just fix to the I want to be. That's fine. So there's repetition in the book. But back to your point, it's those two things: it's the support conditions and effective thickness of the glass.
I was surprised to see the stiffness modulus was 70 kilonewtons per square millimeter. That's the same as aluminium.
Yeah.
It's quite high.
It is quite high. It's brittle.
And
that's the brittle the problem.
And just another point, they have used an enormous amount of structured glass in multi-story buildings in America. Is there a code available in the States?
No.
That you could put on?
No. There's a code in Australia that only deals with monolithic glass. And we've used that for design of beams.
I'm just surprised they wouldn't have.
I know. It's extraordinary. Canada doesn't have anything. No one really has anything definitive. And in fact, the world is, I've been told, and we had people from all over the world going, we're looking at this book, that we're looking at this book as a launch pad for our own. And the Eurocode, the people who are writing Eurocode helped us draft this because they know that they won't be done until 10 years in there, how long they take. So they said, well, can we just put our ideas into this? It wasn't just me, it was a 17-member group said yes. Okay, fine.
The factors, I thought your partial safety factors, I would have expected them to be higher.
Yeah.
You said again quickly.
Yeah.
Okay, thank you.
I'm just interested in, you talk about the difference between the load durations and stuff, and you showed the different design scenarios for different load durations. What about cyclic loading and fatigue type failures for glass? Is it like similar to a critical crack length in stress corrosion cracking in steel, or how do you deal with cyclic loading? Fatigue type failure.
That's part of the load duration that is sort of built into that. I mean, you've got pedestrian loading and the gusts and that sort of thing. It's actually part and parcel of that.
Okay, so that in those factors.
That's where those factors really come from. It's all about brittleness and how it impact load as opposed to.
Sorry.
Just one question about your work example. Obviously, the Young's modulus is a lot better for glass than I thought, but would it be typical to assume a span depth ratio of 250
For floors, yes. But for other elements, it can be span over 65. For cladding, there's a whole section, again in the book, says which span to depth ratios you should use for which element, depending on what you're doing. So for floors, it's that. For beams supporting cladding elements, it's much higher, span over 65. The CWCT guidelines are repeated as well, if you're familiar with those, but they've got lots of text and guidance on effective sort of deflection. But if you're designing a structural element, a structure made out of glass, it just happens to be made out of glass. A lot of the rules and governance that you use for other materials pretty much governs there, because if you're doing in fact, we actually designed a conservatory using the rules in the book to make sure we tested it, see if it actually works. And a lot of the rules you apply to any other conservatory or cell structure would apply to the glass.
I would imagine for a floor, use 360 would be typical for a Britain.
No, they really did. It was 250 was the governing, because they included in dead load and closed load and that sort of thing. So.
Sorry, just a quick question there. I have. It would seem to me sometimes that the connections would be the governing factor, especially on frameless glass.
Yes.
Have you a special way of dealing with connections or design for design?
The thing about connections is ultimately we've got some hand calculation guidance for localized stresses within connections, like spliced connection detail and just standard bolt connection detail. But ultimately, we do recommend in the text that you have to use finite elements eventually, because of the localized stresses around glass. Because you have to have material that has a very young modulus to allow it. So if you have it right against steel, it will crack because it won't allow it to expand and contract and yield.
Yeah.
So there is some guidance, a lot of guidance actually, but ultimately it gets down to the nitty-gritty of designing the connections. We have to defer to finite element analysis.
In shearing and stuff like that.
Yeah. And you have to. We also talk a lot about testing, prototype testing, verifying, because there's no code of practice. Local authorities, especially in Germany and countries like that, and Hong Kong, they say, okay, that's great. Now I want you to do a complete load test or testing to prove that what you've designed here is actually valid. So we talk about different types of testing, whether it's visual strength, verifying your own design, that sort of thing. So, and there's a whole codified approach about how you test things. They've gone that far, but haven't actually gone far enough to actually say this is how you design in glass.
Eddie?
You mentioned there about the difficulty of dealing with the fact that laminates don't line up properly.
Yeah.
When a lot of the load will be applied through connections, which are drilled holes in the glass, would those drilled holes be done pre or post lamination?
It's pre. You can't, especially if you're doing toughened glass, because you have to do that.
Yeah.
You can't drill into toughened glass, because if you do, clearly the pre-stress will go, bang, off it goes. So you
can't even line them up with that?
No, it's very hard. Yeah.
I just noticed that your top layer was toughened and then you dropped it to 8 mil. I assume that you have to allow for somebody maliciously trying to break it, like dropping a lead weight or something.
Yeah, you don't know. It could be. You're right. I mean, a lot of glass failures, when you get called out to inspect something, typically you'll find it's an impact load that someone's hit it. Some cleaner has hit it with a bucket or something like that. A client would normally say it's nickel sulfide, but yes, typically that's what we've got there.
What would your minimum top layer be? And it would have to be toughened, I presume.
It can be toughened. It doesn't have to be. You could just have it heat strengthened as well. You can have it entirely heat strengthened, or you could have it all toughened. It's about risk assessment. I mean, that's the other thing that would come out in the text, is that especially when you're doing balustrade, it is actually possible to do a single monolithic glass balustrade with no handrail on top of it, just like an arrest edge on top of it with but you have to do a risk assessment on it. And that goes with all structures pretty much. We've just released a text on risk assessment for structures, for high risk structures and generally for structures, and definitely applies to glass, because if you're doing a glass balustrade with no overhang, or you're just doing it to demark out some area that no one can actually fall through, then it fails, so what? You always ask that question. If something fails, so what? What happens? What's the consequences? And then work your design based on that. it's, you know, what we were doing here is the toughened glass system and having that on top and having it structured at the bottom was really about holding it in after it's gone. I'm sure you appreciate that.
So it's just about getting the client on board, telling them exactly what the risks are.
Yeah. Looks fabulous though.
One of your slides showed a wide range of characteristic strengths on a basis of 740 samples of glass, and I was just wondering if was there a Euro norm for manufacturing the different types of glass?
It's a worldwide one actually. Yeah. There is a lot of talk about, in the US they don't call it toughened, they call it tempered. They call heat strength and semi-tempered. But then their actual limits on strength is actually different. There's for toughened, I believe it's 69 units per minute squared as opposed to I think it's 120 we've got for hours. It's different sort of varies values, but the values that are expressed in the book are those for the Eurocode, and it is explained as such. And they've been used for decades. Those values, they come from testing and that sort of thing. And but over the years, there is some talk of calibrating that. Additionally, something on the partial factors, the glass industry is pushing for the gamma G for dead load, for self weight, to be reduced for glass because of its uniformity. So rather than 1.35, we can have it down to 1.1, 1.2. And that's something we actually talk about in the report, and you can actually justify that because of the uniformity of the material. But, you know.
Well, gamma M, the material strength factor, I know, as Mark mentioned, it did seem that it was quite a low partial factor of safety for the material itself, given the range of...
I know, but that's what they've adopted. You've got to consider that all the other partial factors have been applied to it.
That's true.
So it's a combination. We did have this conversation in the steering group.
Sorry,
yes, there is, yeah.
Are you seeing more or less nickel sulfide failures?
We just had one a week ago. Where was it? It was near London Bridge. I wish I could share it with you, but I can't because it's confidential. But it's as time goes on, yes, you're going to get it because that it's embedded in the glass. You don't know it's there until 10, 15 years after it's installed. It's going to happen. I can't give you a definite statistic. It is very, very rare. And you can do everything you can on a heat soaking I told you about. That can actually do a massive impact on reduction and the risk of it happening. But it does still happen. There's nothing you can do about it. And that is why we have all these redundancies. Redundancy in glass is, it's key.
And so when you go back and say to a client, there's nothing you can do about it.
Yeah, I know. But you can turn around and say, it's very, very rare. You can show the statistics and do everything you can say, look, this happens extremely, out of all the glass structures that happen, it's so rare.
That's a little comfort to that, so does the glass industry insure for it, or what is the comeback?
Yeah, where's the liability lie or responsibility lie?
Yeah.
That's the manufacturer. It's definitely the builder and the installer, the contractor. The contractor, the specialist contractor buys that risk.
Specification and the testing.
Yeah, that's what it's their risk.
And that goes back to people like Saint-Gobain or people like that, as opposed to the window people or the framing people that we know of here.
Yeah, this is talking about the actual glass itself. There's nothing you can do. You can't induce it.
Yeah.
Design. It's not a design latent defect. It's not a fault of installation. It's the material. It's like a glass beam exploding, or beam exploding.
And Chris, is there an expectation that the glass laminates will fail at a certain point or a certain age?
Not the laminate. The century glass deteriorates over time, but the PVB starts off as it is with its low shear capacity and remains that way. I'll show you that chart again, maybe. But I'll just
those curves, do they level out, or are they just?
They do, yes. They just level out, or they converge actually. For the 50 degree, here it is. So I'll raise this fellow up again. Okay. So for the 20 degrees, even after 10 years, it's still quite strong. but eventually you can see there's a downward trend. Eventually it does converge, but the laminate remains that way. PVB laminate, which has been used for decades, has always been that way for perpetuity. They've been using it in cars for hundreds of years, literally. So it's not a problem really.
It's interesting that you say it's the glass manufacturer, because very often it's not actually the cost to replace is not the material, it's the accessibility
Yeah.
to get you back up to the
Yeah, well,
point at which.
I know, and it's that buildability. There's something we talk a lot about in the book about buildability. It's very important about maintenance,
Yeah.
about how you inspect glass, because you're going to get called out on glass structures like what I'm looking at here. We give some guidance and advice about what you should be looking for. The nickel sulfide thing won't go away anytime soon. We're doing everything. The industry is doing everything it can to reduce the risk of it occurring. It is a very, very small risk, but it can happen. Best will in the world, heat soaking, what have you, it can still happen.
I think we might just take two more if you don't mind. We'll wrap it up then. Sorry.
Just on the heat soaking, is that doesn't seem to be a standard. It seems to be an extra that somebody gets annoyed when you ask for it.
No, where you have to justify it, because it is quite expensive and
It is expensive.
yeah, it's expensive to do, to actually make the sheet again and then heat it again, and also to have this to failure. What you do is, if you had small sort of panes, then why are you doing it? Because the risk of it actually, the nickel sulfide being in there, is very low. But if you've got very large, like 18 metre long bits of glass, which now exist, you're going to do it. Again, it goes back to risk assessment. Thinking on those sort of lines. What's the risk of this happening? What do I do? What mitigating actions going to do to reduce this risk? One of them is heat soaking, if you're using toughened glass. By the way, it doesn't. Nickel sulfide doesn't really happen to heat strengthened. It's only toughened.
I just wanted to ask when the document's going to be published. Cause
January 2014. It took 18 months of it's a hard slog to get it out. And what you see there, all the charts and the tables, were extracts from the final typeset version, which I got about 2 weeks ago. And I sadly covered in red. But anyway, it's coming back to us now, hopefully this week, for me to give my one more sort of scoot over and then get it out the door for January.
Is that the public comment time span you're talking about?
Sorry?
Is that the you're saying it's coming back to you in the end of the month, or?
It's coming back to me to review the final, because I keep on having to review the text that's been the typeset text.
Yeah.
So it's been peer reviewed. It's finished. It is finished. It's just I've just got typeset. It's just admin basically.
But it's just the end of the PR period on it.
Yeah, that was about a month ago. So over 6 weeks ago. But we're just trying to get the typesetters to do it. It's a lot of work. It's over 150 pages long. So the glossary in it is extraordinary.
Because just so I suppose on behalf of everyone here, I'd like to thank Chris for his interesting talk and for sharing his enthusiasm for the document with us.